able to arrive. But just for those of you who don't know, I am Hewlett, David Hewlett, and I'm here with my I'm with Genius chats, and very, very excited today because I've got my good friend and, as it turns out, genius, Ari Berman, CEO of BioTeam. And I'm trying to think, we got in touch because you offered to explain, I can't remember what was it high-powered computers or was it the bio side of stuff we met on Twitter with?
It was a couple of things. You reached out to me. Well, so you followed me on Twitter.
Yeah.
And I'm talking about Twitter.
Back in the Twitter days. That's right.
Back in the Twitter days. And I reached out and I was like, "Hey, thanks for the follow." And you're like, "Sure, I love tech." And I'm like,
I'm a nerd.
What I know. You're like, "What's a supercomputer?" And then we started talking, and the rest is history. So.
Well, as soon as you put super in front of computer, you got the funny thing for me was what you're doing that was so fascinating to me was you're bridging the kind of the more traditional life science, not traditional, but the life science stuff that's going on in the real world with these massive, computer clusters and supercomputers. And as you put it, and I love this term, and I've used it, I think, in the chat, in the text as well, is you're making science faster. Maybe you could explain that for people what your company's up to.
Yeah, I mean, so we're a consulting company that really does exist. Our goal is to make science go faster.
Right.
And we do it through a whole lot of things. One of them is through supercomputing, and creating high performance, computers and storage and networks and cloud environments and all of that, which sounds very IT, but it's not. It's scientific computing.
Right.
And then also working with data and trying to help life sciences with their data, because data is literally all over the place. It's the Wild West in this field.
And they seem scared of it. Like, I feel like they're almost, it's so funny to see scientists who are so smart in whatever their fields are. They seem to sort of shy away from this, there's almost a fear of the IT side of it.
Yeah. Well, so it's interesting because a lot of, scientists in the life sciences area, healthcare providers, those sorts of things, they weren't trained in computer science. They weren't trained in how to use advanced computing at all, right? So what they were trained to do was to be in a laboratory and use very complex laboratory equipment to answer questions no one's ever thought to ask about biology and about humans. In an effort to try to make the world a better place for everybody, right? And they didn't know that they're going to buy a microscope that can generate 5 terabytes of data overnight. That's a lot, right? That's, most people's laptops these days are maybe 1 terabyte,
right?
And and then they're like, well, where do I even save that? How do I analyze that? They don't know. I kind of joke, and I apologize to the scientists out there, but I sort of joke that they can barely do email and print things.
But that makes sense though, because there's so much of their time is used sort of in the field, so to speak, or in the lab. I mean, it's a whole other set of skills, right? Isn't it? I mean, or do they learn? Is programming something that comes up, or science? I guess there's certain science.
So programming does come up. Data science is a big part of our field now. There's a specific sort of subgroup of that called bioinformatics. It's the science of biological data.
Right.
And so they are quite sophisticated. They do a lot of programming, and they use a lot of supercomputers, a lot of cloud environments. Set up their own analytics environments, things like that.
And are they sitting right between the two of them, or are they doing the science as well, or are they more IT? Where is bioinformatics in that?
No, they're scientists. They're PhD scientists,
right.
And they're doing their own research. However, most science organizations these days have like bioinformatics core groups, like services. Where bioinformaticians will help others do their, join in their research essentially and help them analyze it.
Right.
Which has become kind of a bottleneck for things, but because you can't do modern science without advanced computing. You just can't do it.
Really?
Yeah.
So
Yeah,
I guess that makes sense when you're creating that kind of volume of data, and I guess the tools that are the tools and all the technologies that are being used in the lab. If you bring in a new piece of machinery, that's going to be creating data 100 times more than whatever the last one was. I mean, we're not writing it down by hand anymore, right? It's all
No. Back in the days when we used to literally cut out the area under a graph and weigh it to get the volume, to get the area under the graph.
Oh, wow.
Yeah.
Oh my God, seriously?
Yep.
Wow. We're dinosaurs.
Dinosaur, old.
How did you get into this? What was because you've got the brains on the wall behind you. That's because that was, you were studying the brain. That's how you started, wasn't it? Or was it molecular?
Sort of. If you go back before that, as an undergrad, one of my good friends and I built the first what's called Beowulf cluster in the state of Texas in 1995, I think. And it was out of a bunch of Dell workstations. And a Beowulf cluster was the first, it was a concept that was developed at around the same time, 1994, 1995, when Linux came out for the first time. Red Hat Linux was the first, right?
Yeah. I remember downloading the diskettes one at a time off the internet.
One at a time. Yeah. There were like 7, I think, on the first one, right?
Yeah.
But basically it was a supercomputer doesn't have to be all bespoke, crazy hardware. It can be anything that you can network together and run a problem across all the computers, right?
The cluster compute. That was the first time we were doing cluster computing. Is that
exactly right? Before that, supercomputers were all vector processors and the Cray XP one, those types of things. The first Cray supercomputer. There were no transistors at that time. It was all just wires and cables that created these transistor gates.
Right.
It was kind of crazy. So,
so your first love was the computers.
Yeah, it was. At the same time, my undergrad was in biology. I've always really liked biology, and when I got to graduate school, I ended up gravitating towards molecular biology and neuroscience. I've been affected in my family by Parkinson's, Alzheimer's, strokes, things like that. My grandfather had advanced Parkinson's and and Alzheimer's together, and died of that. And so, part of me was like, I kind of want to solve that problem if I can. And so, I ended up in neuroscience, which turns out can have a huge computational component. Where
they're pretty complex computers already, aren't they? I mean,
it's crazy. I don't know if people know this, but the number of connections in one of our brains is 400 quadrillion. That's more than known stars in the universe.
Wow.
In each of our brains. So there's a level of complexity there we do not understand. We'll probably never understand. Do you think it's just a limit of our brains? Like our brain just can't understand our brains type thing? Or you think it's just too complicated? It's just a matter of the processing. We don't have the processing for it. I don't think we're able to comprehend it because we are it.
Right.
It would take some sort of a superior being or something to comprehend how all this works and understand how consciousness and self-awareness emerges from that.
I'm reminded of that. There's a book that I guess a geometry book called Flat World. Remember Flat World, this book?
I do remember. Yeah.
The idea that we could, as a two-dimensional being, couldn't conceive of that third dimension. Like maybe our brain just doesn't allow us to have that extra perspective on what we are and what we do.
Yeah, it kind of reminds me of A Wrinkle in Time.
Oh, yeah.
They went to the two-dimensional planet, and then they went to the planet where no one sees anything, and so there's no color.
Right.
And, they wake up in the warm, and they go to bed in the cold, right?
Which makes, I guess that doesn't make sense, doesn't it? All right, so you're delving into the mysteries of the brain, and you were studying addiction and stuff as well. Right? Is that not a part of the?
Yeah, my graduate work was on addiction because addiction is very much a part of my family too. Alcoholism, those sorts of things. So my graduate work was on alcoholism specifically. Trying to find genetic linkages to the inheritance of addictive behaviors.
Oh, wow.
Because it definitely can be inherited. The problem with genetic behaviors is that they're very, very complicated. It's not like you have the alcoholism gene. It's like,
Right.
no, you have the 4,000 alcohol genes
Right.
that kind of come together and produce this type of behavior. And so,
Yeah, I really thought that gene thing, I thought we were so onto something, and we totally are, except that it's not as simple as like, oh, there you go, the blue eyes, green eyes. It's not as simple as that, is it?
no. It's very complex traits that come together because we're not peas. So it's.
I know there are days I feel like maybe I am, but yeah.
Oh, yesterday I was totally, but I just needed to be watered and that was fine.
Yeah, that's a little sunshine. Yeah, yeah, I know those days. Yeah. Where did you study this? Where were you studying this?
University of Texas in Austin, and that's where I got my PhD. And there's a group here called the Wagner Center for Alcohol and Addiction Research, and that's where I did it. Pretty awesome. Learned a lot. Learned enough to help my dad. Recover from his alcoholism. And so,
really?
Yeah.
You got him to listen to you as well. I mean, is that so? Part of it, I guess, is because I mean the issue that because it's obviously it's our family as well. The issue is you can't. How do you convince someone that they've got a problem when they don't want to know that?
Carefully, right? So I tell people a lot. One of the most complex things about the human brain is that it's the sensor that tells you when things are right or wrong. When it's wrong, it's not telling you what's wrong.
Yeah.
It's one of the weirdest things about, say, depression or even anxiety, right? Is that you just know you're in a bad mood. Things suck. In general, they suck. You're not consciously aware of your depression until you become aware of it. And once you're aware of it, then you can isolate the behavior, then you can work on it. Same thing with anxiety. People with anxiety, eventually days are like, oh crap, I'm having an attack again. Now I know what's going on. Then they can ground themselves. The same thing is true with addiction because, addiction is an externally induced neurological condition, caused by strengthening and weakening certain pathways in your brain by the substance you're using. And, when you use it a lot, your brain tries to change how it works in the presence of, say, alcohol, so that it can operate normally, right? Which is why alcohol has a lesser and lesser effect as you drink more and more of it, longer and longer, and you have to drink more to get drunk, essentially, because your brain's trying to adapt to work normally in the presence of that. You take it away suddenly, and it doesn't work anymore because it's adapted to work in that's addiction.
Wow.
Your brain then tells you, in extreme addiction cases, you are going to die if you don't get alcoholism. That's what it's telling you. It's not true, but that's
if you don't get alcohol.
Yes.
Yeah. I see.
Alcohol. If you don't drink, your brain is already operating somewhat normally under the presence of alcohol. You take it away, and then suddenly it doesn't work anymore.
Right.
And so your brain's like, we need alcohol. We gotta work. And so. And so your brain is not aware of it. So the behaviors that happen are the alcohol seeking and all the social damage that happens from it, and all of those things are a result of your brain just trying to function normally. And in order to recover from any neurological condition, you have to become consciously aware of the condition and accept it. And that takes time sometimes. And so with my dad, actually, we went to lunch and I sat down and I started explaining just the neuroscience of addiction, much like I just did,
right.
With some more details. And he's like, "Oh crap, I think I have that." I was like, "Yeah, you do." And he quit cold turkey, relapsed once, and has been clean since. So
really good for him. Jesus.
Yeah. He's also a scientist. It's a geologist. So
that helps too, I guess. The science
helps,
brain.
People who tend to be data driven are like, oh, I have data now. Maybe I can apply it. Rather than it's much harder with people who are more emotionally driven because the emotions are what are played on.
Yeah, and it's insidious too. I mean, it's the nature of addiction is it's amazing what you. I mean, I think about my days when I used to smoke or try quitting smoking, and I would sort of. I'd go out for dinner, and you'd have a cigarette, and you go, "Oh God, I've started smoking again," and then I'd be smoking, and then it was at some point I suddenly went, "Wait a second, That doesn't mean I had a cigarette. It doesn't mean I go out and buy more cigarettes because I've started smoking. Like, it's just your brain is so good at tricking yourself into these things. You know, yeah. And the alcohol thing, I'm convinced is we just keep getting more and more information about how just wretched it is for you. You know,
it's not good for you. Yeah, it's and not everyone can become an addict either.
Oh, really?
Do different things. Yeah. So.
So there are people who are immune to not immune to the effects, but who aren't immune to the addictive effects of the alcohol.
I'd say there's no such thing as immunity, right? If you really try hard, like you are just drunk 8 hours a day for 3
really
years,
commit. If you really commit to
it.
Yeah.
At some point, physics takes over, and you have to really want it, right? But in general, the behavior, the sort of the behavior patterns that are associated with it, with addictive personalities, you know, those are somewhat inherited. And then there's a lot of environmental factors that lead up to it.
And so you're studying the brain, you're studying addiction. I'm assuming there's a lot of data involved in that, and that the computers come into play. I'm assuming is that where it went?
This was a long time ago, but you know, some of the supercomputers that I helped design and build at UT Austin, I had collected what for the time was a lot of data. Now it's kind of laughable. A whole terabyte? Oh no, it was less than that.
Oh, was it really? Oh, wow.
I had something like 2 million data points on you know, genes that have been turned on or off or switched up or down and stayed up or down in mice models when they were exposed to alcohol for a long time. And to tease it apart, I did use one of the clusters that I designed and, you know, programmed in Perl.
Oh my God, Perl!
Perl.
Oh, I used to love Perl. That was all web design stuff, though. I didn't realize they were using it for that kind of stuff. I'd only ever used it as because it was good at text, wasn't it? Wasn't it good at sort of processing text or something?
It was good at almost everything. Like I'd written a fully parallelized data processor, you know, that works on a supercomputer that took a big problem, divided it up into little pieces, farmed it out to other servers, processed it, and brought it back. That's what supercomputing is, right? It takes a big problem and slices it up into pieces, processes those pieces all at once, and then pulls it back together.
So it's not so much a matter of throwing sort of metal at it; it's the machine at it. It's like you've got to actually be able to separate that into chunks.
Yes, and there's various levels of parallelism. So, you know, there's it's kind of funny. The field has this term called embarrassingly parallel, which is literally you just chop it up and run them individually and it'll still work, right? And then
I love nerds.
I know, they're great. And then there's really challenging parallelism, you know, where you know, simulations are really challenging parallelism because you know, the edges of your simulation have to communicate with each other, and so you've got these processes off on different computers. And, you know, when you get to the edge, those edges have to talk to each other. And so there's a lot of process communication you have to have between those. And so it's not perfectly accelerated by splitting it up 1,000 times. There's a limit to how far you can scale it because of that. But those are really, really hard problems.
Is that stuff, I mean, that sounds incredibly sort of manually intensive, like trying to figure out or are there programs to write the programs to do this? I mean...
No, there are really well-established parallelization paradigms in supercomputing programming. There are, you know, libraries that you just include in your code. It's called MPI, you know, message passing interface is what it's called. And that actually governs being able to, okay, so I'm going to enter this loop that pulls in this data, and I'm going to do it 1,000 times, and each one's going to spawn on a different machine, right? MPI sort of handles that with a scheduler in the background that's helping coordinate it all.
So is that like with networking? Basically, there's like that you can have what is it? Is it TCP? Is it TCP that automatically organizes this, putting things into packages and all that?
TCP does over Ethernet. That's sort of the TCP/IP is the language of the internet.
So is it the same kind of thing happening, but with the processing on the?
It depends. Actually, not really. There's lots of different types of networking.
Damn, I thought I was so clever.
Well, you can do it that way, right? But
It
if
would be embarrassing, but it would be, yeah.
no. People run with this now with like
Right,
really fast Ethernet,
right.
really fast networking because, you know, I don't know the network to my house is 1 gigabit, for instance, right?
Yeah.
And which is great.
Don't
I
you
love
love
it.
the future?
Oh, it's
Man,
great.
God.
Well, they're building supercomputers now with 200 and 400 gigabit network connections
Oh, wow.
to each machine, right?
Wow.
Because the amount of data you have to transmit back and forth is really, really a lot.
But these are short distances, right? I mean, these are the
Yeah,
between the clusters type thing? Is
yeah. It's
yeah.
short distances,
What do
but
they call, is it nodes they call them in the,
no, it's yeah,
yeah.
individual. They're essentially individual computers, servers, and they're just stacked in racks, and then
Right.
linked by a network in the back.
And that's like
When we
TAC. That's where I visited
went to the
TAC.
Texas Advanced
Yeah.
Computing Center, you saw that, right?
Yeah. The picture that I sent out on the internet was actually me holding one of the giant old discs from
Yeah, I
TAC
saw
when
that.
we were there.
Yeah, yeah.
So
Old spinning discs that were the size of you.
Yeah. I mean, it's but what's funny is you talk about how fast the computer technology's changed, but in a way, I've heard you say this before that it's the actual scientific process is speeding up. Like that is moving faster now than even the computers are advancing.
Yeah, especially so in the in the like biological laboratory space, and also in the clinical diagnostic space.
Right.
The level of innovation in those pieces of equipment is far eclipsing, IT technology.
Why is that? Why would that?
We
Is there
just
more money in
learned a
them or
whole
something, or what?
lot. We just learned a whole lot about how to do things really quickly. We had some breakthroughs in, say, in camera technology, for instance, and micro resolution, so genomic sequencing, right? So sequencing the human genome. The first human genome took 12 years and $13 billion to
I remember it. Yeah.
Okay. And there was a public and a private sort of competition
Yeah.
to get it done. Cellular Genomics and then the National Human Genome Research Institute. It's the National Institutes of Health in the U.S.
I can't remember who won. Who won that one?
NIH did, I think.
It was NIH. Oh, yeah. Okay.
But only by a little bit. And
Right.
then we had 2 copies of a genome that we could merge into a reference,
Right.
which was pretty important. But our genome, the human genome, is about 360 gigabases, right? So an A, T, C, or G is a base. And so if you look at each of those simply as a letter, without any other information on it, just your genetic sequence would be 360 gigabytes in size,
Oh, wow.
right? Just yours.
That's just the letter representation of those. Wow.
Yep.
Because you think of text files as being pretty small. Like, so that's.
But each character is a byte.
Yeah.
Right.
No, it's crazy.
So
Yeah.
if you have, 360 million of them,
Yeah.
it turns into a big file.
No, it's amazing.
So it the way that we sequence these things is you take all the DNA out of, say, a cell or lots of cells, and then it's huge, right? There's 21 chromosomes, right? And each of them have lots of DNA on it, and there's 2 copies of each one in every cell. And so they're kind of humongous. The way we did it is you take that giant genome and you cut it up into small pieces that are 20 to 30 bases long, and then we strip it down so there's only one half of it because it's double helix, right?
Right.
And there's complementary bases that create that double helix on the other side, and so in a controlled chemistry reaction, you can add one at a time each base that matches on that sequence. And each base that you match on that sequence has a different fluorescent tag on it. So modern sequencing techniques do this one at a time. So you take
Wow.
these millions of little sequences, literally take one end of it and bind it to a glass slide, and then seal it under a thing where you can wash chemistry over it. And just real quickly, grow that other chain of sequence on the side with different fluorescent tags, and then take a picture every time, and then that sequence of pictures is your sequence.
Wow. I had no idea it was so fiddly.
Very fiddly.
So, and is that an automated process, or is that
It is now.
It is now, but it wasn't back then.
Back then, actually, you had to run it out on a gel, on a big.
Oh, really? The electro gel thing? Yeah.
Apheresis, yeah. DNA is very polar, so when you run it through a gel matrix in a voltage difference, it actually separates out by size along the side of that, and so basically you can separate it all out and do the same thing I just talked about, but with those fluorescent tags, but wait until they come off the end, and so the sequence grows and grows and grows, and so the bigger ones come off slower, and so they end up coming off in order at the bottom, and there's a little camera that takes a picture of each time it comes off.
Oh my God! Literally just watching them extend over the gel or whatever.
Drip off.
Wow. Oh my God! It just sounds so old-fashioned somehow.
It is. That was called Sanger sequencing, and was a whole thing, and it took forever. And now you can do getting over a cold. Sorry. Now you can do a whole human genome overnight for about $500.
And is that because? I guess because they've automated, and not only have they automated the process, but they've also sped up the computing required to process that.
Well, no, the process that I described earlier about, well, this is one way. There's lots of ways to do it, but attaching the little sequences to a slide and then washing chemistry over. It's called a flow cell, and taking.
Oh, that's a flow cell. I've heard of those. Okay, yeah.
That's a flow cell. Yeah.
Okay.
Take a picture every time. That camera technology is what enabled that. And that's well, it was called next generation sequencing a while ago. So we still kind of
it aged badly. Yeah.
It did, because now there's other kinds.
It's like new media. I always love that one too.
Right.
Yeah.
And so anyway, that allowed this to happen far faster, because you didn't have to wait for it to come off a gel. You just do the chemistry, take a picture, do it again over and over and over and over again, and then you needed the computational power to select all the spots, right? Because they're random. They're all over the place. And there's millions of them in one field of view. And so you have to do that. And then the computer has to call which base that is. And sometimes it's not entirely clear. And so you have to do a bunch of different
Well, I guess it's squishy, isn't it? So it's not as simple as just like an on or off.
And then the most computationally intensive part of this, if you don't already have a reference genome like we do for humans, you have to assemble them all back together. You've got all these 20 to 30 base things that you have to figure out in a gigantic puzzle how they overlap, how they fit together. And so you have to reassemble the genome. So genomic assembly is what that's called. And
wow.
Insane process.
That's wow.
Very computational.
But once you've got these things sequenced, you've got a huge stepping stone ahead. Wow.
And so the more compute power you have for things like this, like assembling a genome, you need at least a terabyte of memory, because it all sits in memory.
Wow.
Yeah, it's like RAM memory on a computer,
right.
not just a disk. So
wow.
Yeah. That's where supercomputing comes in.
But but if all of these scientists are requiring this access to these massive computing clusters or whatever, that's not all happening in the universities. It's happening. Is this a cloud thing? Is this something they're doing? How are people dealing with this kind of stuff?
So
this is BioTeam, right? This is basically what you do. Yeah.
The answer is it's complicated. So
damn it, I hate those answers. Yeah.
And the answer is actually yes.
Yeah. Right.
All of it. It's so most universities in the U.S. at least, and I think globally, have their own computational resources. Like some of them run their own supercomputers. Some have giant supercomputing centers, like TAC in Austin.
Oh yeah, my favorite. That's my favorite. Yeah.
I know. Dan says hi, by the way.
Oh, great. Yeah, hi back. I gotta have Dan on here. I should talk to him.
You should. He give a lot of good stuff.
Yeah, for sure.
Yeah, he's great. And funny. Way funnier than me.
Yeah. He had a great speech at at BioIT. As did you, the future of your future thing. What did you call it?
Trends from the Trenches.
Trends from the Trenches. That was it. Yeah.
That's not something I made up. That's something one of our founders made up, Chris Daggs.
Yeah, but you had to get up there and address it.
I did, because he didn't want to do it anymore, so I picked it up and started doing it. And not as well as he did, but it was fun.
And for those of you who don't know what we're talking about, Dan runs TAC, the Texas Advanced Computing Center, and I was lucky enough. Ari invited me to meet him, and we hung out there for a while. It was amazing, just amazing.
Oh, it's a really cool place.
Yeah, it's like nerd paradise. You're surrounded by computers. I mean, it's just like something out of the Matrix. Yeah.
Oh, totally, absolutely, and it's even if you don't know what you're looking at, it's still cool.
Yeah. It's just
the science they do there is amazing.
I guess I should ask this. I should have asked this earlier. But what defines when you talk about HPC or like high performance computing?
Yeah.
What is there a definition for that? Like, I mean, I got a nice gaming computer. Is that's not? I'm guessing there's a distinction, right?
Okay, well, it's a good question. I'm not sure anyone still has a good answer for it. Because there's lots of different kinds of computing.
Okay, so it's a loose definition then. All right, okay.
Supercomputing basically is anything that you can't do on one computer.
Okay.
It's a problem that's too big to do on one computer. It can require, parallel computing, like I was talking about earlier, or it could just be you've got millions of individual processing things that you have to do over and over again. So you need the capacity more than the capability of a supercomputer. So there's capacity supercomputing and capability supercomputing. And capability computers are things like the Anton supercomputer that was developed by D.E. Shaw, which was made specifically for doing molecular dynamics simulations, which is proteins interacting with each other, or small molecules interacting with proteins. This is a way to short circuit the time it takes to find a new drug. So you can take a bunch of virtual small molecules and interact them in these simulations. And so that supercomputer was designed with specialized chips that know how to do just that. And they're called ASICs. And it was a technological marvel.
So it's like a GPU only specifically for how to model these.
For simulations. It's very specifically for them.
Wow.
So it's not generalizable. You can't do anything else on it. You just do that, right? But it does it orders of magnitude faster than anything else.
And they're creating actual, like literally chips for this?
Literally chips, yes.
Wow. So that's got to be expensive.
There are ways to do it. So there's two types of sort of chips out there that you can program, right? To do certain algorithms. Some of them you can program once, and those are called ASICs, and I'm forgetting what that stands for. And then one that you can reprogram over and over again is called an FPGA, which is it's called I think it's field gate array something or other.
And notoriously hard to program, if I remember correctly.
They're really hard to program. Like you have to understand processor design,
right?
To do it. Then you use like a hardware descriptor language. Field programmable gate array is what FPGA stands for.
Wow! So you're basically programming almost the physical layout of a chip as you go type thing.
ASIC stands for application specific integrated circuit.
Ah, that seems like an overly complicated. They could have, I feel like they overdid that.
People like their acronyms.
They do. They love their acronyms. So true. So true. All right. I know I'm bouncing around all over the place, but we've got to. So you've got to this. I know. I'm notoriously bad at this, but you have gone. You're obviously your BioTeam now. How did you make the jump from, university and studying the brain and addiction to this sort of intersection between science and computing?
Well, I did 2 postdoctoral fellowships afterwards in San Francisco. One was entirely in the lab, and one was entirely computational.
You just couldn't decide, could you?
I'm like that. It's ADHD, man. It makes you want to do everything.
Why do one when you could do both at the same time? Yeah.
I mean, you've got every kind of project sitting behind you there, right?
Yeah, all of them unfinished, I might add, but yeah.
Exactly, precisely.
Yeah.
And that's the best thing about science is you're never done.
Yeah, exactly.
The second one was computational, and so it kind of started bringing things together. The professor I was working for there, Sean Mooney, it let me build a small cluster for the lab, and we were using it because we were doing entirely computational work. And then I went to give a talk on some of the things I did there in Boston, and this company called BioTeam was in the audience, and actually someone who helped found BioTeam was in the audience, and he tried to hire me at the Broad Institute, but my wife didn't want to move to Boston, and so he passed me on to BioTeam, and the rest is kind of history. So I joined as a consultant in 2012. And
wow, I didn't realize you've been there for so long. That's amazing.
Long time.
I mean, they're a great bunch, I got to say. You
got to meet a lot of them. Yeah,
they know how to have a dinner party for sure.
Yeah.
Okay, so you now are you in that situation where you're finding yourself? Are you moving out of the tech stuff and in more into the management side of stuff now, or the business side of stuff, or do you still get to play with what I would call the cool stuff?
I would say that I keep up with the tech, but in actuality, my real title is Chief PowerPoint Officer. All I do is give presentations and be on Zoom meetings, and
I got to say, if you're damn good at them, so that's probably the problem. Is you're good, if you sucked at it, you could probably be doing something else. But yeah, no, because you've had a number of talks that I've listened to that are just amazing. Everything from AI to high power computing stuff. I mean,
Well,
you enjoy it though, right?
I really enjoy it.
Yeah.
I think my graduate program at UT, actually, I don't know if anyone's listening, but they forced us to do 5 semesters of learning how to give talks, which is critical. For any field in which you have to communicate, which is most of them, it's really critical. So that was good, and then a lot of people telling me what I was doing wrong over the years, which is helpful.
Yeah, that was good. A little criticism. And what do you see? Like, I mean, looking forward. I mean, where do you see this stuff going? I mean, are scientists going to come in knowing that the computing side of stuff is things that they're going to have to do, or you think there's going to continually be this sort of split between the two?
I think there might continually be a split on some level. So I just came back from the Supercomputing conference.
Rub it in. Yeah,
I know you were supposed to come.
I know.
You're coming next year.
I know, next year for sure. Yeah, I don't.
Okay.
Yeah.
It's in St. Louis next year.
Oh, is it really? Oh, great. All right, fantastic. Okay.
Yeah. So.
Never been. So another good reason.
Yeah, definitely. Good barbecue.
Yeah.
So I just got back from that conference, and it's probably one of the premier nerd fests on the planet.
Really? Yeah.
It's like Comic-Con except for like tech nerds and scientists.
See, I can't. You're the second person to tell me. One of them the other guy was a physics professor, astrophysics professor at University of Toronto, who's the same thing. He's like, you gotta go. It's magic, man.
Yeah. It's pretty awesome, actually. This year was the biggest one ever. We had 17,000 people.
Wow.
That's not the biggest conference I've been to. The biggest one was the Society for Neuroscience meeting. I think that one got to 38,000.
Really?
But, yeah.
Wow.
Yeah, it's impossible to navigate at that size. But,
and are you there like with BioTeam, or are you there just because you want to keep track of what's going on? Or
no, I was there with BioTeam. And our new parent company, N Squared.
Oh yeah, that's about that too.
It was pretty awesome, actually. We had a really, really great time. It's so clear how much we can do together, and that's something that BioTeam's always been. Not to go down another rabbit hole here, but
yeah, why not?
There's power through collaboration, right? Working together. You can do more collaborating with people than each one could do separately.
There is a tendency for us to want to go off and do our own thing, though, isn't it? I think it's like almost a nerd trait that we all like to do our own. I see it a lot with in the disability space and the accessibility space, where you've got all these brilliant engineers who want to design the next greatest wheelchair or whatever, but they're working in a vacuum. They're working in their own little sort of isolation on stuff.
There's a lot of incentive to work that way, right? Especially in publicly funded sciences, because here in the U.S. the NIH funds 85% of life sciences research.
Oh, really?
And they determine whether people get grants or not based on how productive they've been as an individual. So they're incentivized to do their own thing. The other flip side of that, though, is that there's a bit of personal glory in it, right? Let's not deny the ego part of these things, right? I want to be first to this because I'm going to be recognized, or I'm going to get rich, or I'm going to do whatever.
I want something named after me. Yeah, exactly. Yeah.
Something named after me.
Yeah.
Versus, you know what? Let's do it because it's the greater good. Right? Let's do it because the world can be a way better place than it is. Let's get there. Right?
Yeah, but you can make the world greater and get credit for it. That's even better.
That's even better. and if you can make the world better, and the world just kind of recognizes it without you having to put yourself all over everything, that's the best. Right?
Yeah, that's pretty good.
That's where it's really good. So credit where credit's due, right?
Did the pandemic change any of this? I mean, did you find that people were sharing data more because of that? I mean, certainly in the medical sciences, you'd think that would open things up a bit, or not, or did you close them down?
The pandemic pretty much changed everything. I think everyone knows, right? But in our area, in life sciences, biology research, biomedical research, the labs were closed. Everyone went home, and people were wondering what the heck they should be doing. And they're like, "Oh, you know what? I've got 20 years of backlog data. Maybe I'll start analyzing that." And so everyone jumped on the supercomputers and tanked those. And
oh, really? Took them all down?
Oh my God!
Everyone working from home?
Yeah, everyone was working from home, and most organizations, like their VPNs were completely overloaded because they only built them to handle 10% of the population, not 100%.
Right.
And so there was this whole wave of stuff, and then because again of the pandemic, after a certain amount of time, you couldn't get new stuff. You couldn't buy new computers. The supply chain was shut down.
Yeah. I remember that. They were so expensive. If you could get them, they were just gouging you.
If you could get them.
Yeah.
I had to buy a car during that. That was a whole special thing. But,
you had to buy a car during the pandemic?
Yeah, because I hit a deer and trashed my other one.
Oh, God.
So I had.
Yeah, because cars were impossible, but mainly it was because of like tiny little processors and stuff that couldn't get
the chips.
Yeah.
And so, those values went. Anyway, all that happened, and so what ended up happening is the commercial clouds launched a brilliant marketing campaign, which is, can't get to your data center? Bring your credit card over here. Let's do science in the cloud, right?
Right.
which is totally valid and worked, and in a lot of ways kept science going forward, right? But they. Everyone sort of migrated to the cloud because humans tend to be absolutionists.
I know that feeling.
Oh, we're not using on-premises anymore. We're going to go cloud.
Yeah, just cloud. That's it. Yeah,
that's what we're doing.
Yeah,
and the famous Star Wars quote. Only the Sith, think in absolutes.
So scientists are basically Siths. You're saying, yeah.
Pretty much, yeah.
I mean, it does look. It sounds like a dream, right? I mean, you don't have to worry about any IT problems at all. It just works, But it's still someone else's computer, right? I mean, it's still just someone else's computer.
Yeah. You get the bill, and it's like, oh wait, maybe that was a mistake.
Right. Right.
And because you can use the cloud economically, 100%, but it's so complex, and they charge you for every little thing, and fractions of cents. They charge for, but it adds up over time, and so then people started pulling back when equipment started to become more available. Now people are starting to design and build supercomputers on premises again, and we're pushing to do both. Don't go all the way, do both, because then the thing on campus you don't have to make as big because you've got the capability of the cloud to bolster it. And you can use them in an application specific way, and that's
so like the ASICs type stuff makes sense to build your own, have it there, but then the other stuff you farm it out to the cloud or whatever.
Yeah, I mean, the cloud's not some magic place. It's just someone else's data center with software tools that accepts your credit card.
Right. And is it generally way more expensive for the cloud? I mean, because
No, it depends on what you're doing. If you're operating a cloud environment like you operate your data center, it's going to be at least 10 to 20 times more expensive than your data center. Period.
Wow.
Because it's not designed to be operated that way.
Right.
Cloud is designed to be orchestrated. Grab things when you need them, shut them down when you don't, and to use services that aren't actual servers. They're serverless. Of course, they run on servers, but I want to do this thing. Okay, I'm going to hit this service on AWS, and it's going to do the thing, and I'm going to pay for doing the thing, not the servers that's running it.
Right.
And it's got all this orchestration in the back end that does everything you need, and so it does simplify things. The problem is it's a very complex environment.
And it's complicated from a billing standpoint as well, too, isn't it? I mean,
Very, Detailed billing on Amazon is a special kind of torture.
Oh my God, I can't even. I go to. I mean, this is that I've been threatening to bug you about this for ages because AWS is. Even their marketing, like I feel like I need a degree just to go through their marketing materials. Like I don't even know what between their Glacier and their whatever the hell all the different terms they've got for this stuff.
Yeah. Oh, and there's a bunch of other clouds out there too, right?
Yeah, Azure and all that.
Azure and Google Cloud and Oracle Cloud's a real thing and pretty good actually.
Well, I was using the Google Colab stuff, which was great. It's fantastic. Yeah. Just sort of spin it up when you need to, and it's it was pennies for what I was doing, but it was just that was just some it was some Stable Diffusion stuff I was playing with it for, I think so.
Yeah, back to your original question though.
What's
a picture of this look like? Because that includes it.
Yeah.
What's both amazing and terrible about the world right now is AI. It's amazing because it's driving a lot of innovation. It's driving a lot of awareness of data. It's in the public consciousness in ways that it hasn't been before, even though it's a discipline that's been around for 60 years.
Yeah.
ChatGPT sort of brought it to the forefront of everyone's mind, even though they've been using it forever to unlock your phone with your face.
Right.
That's AI.
Yeah. Or check their grammar. Yeah.
Or all those things.
Yeah.
Right? Exactly. And so that's a good thing. The worst thing is that, I was walking around this very technology-heavy conference, and there wasn't, except for ours, there wasn't a single booth that didn't have AI somewhere in it.
Yeah.
Right.
Yeah.
And
it reminds me of crypto. It's got that kind of crypto feel to it now.
It's kind of replaced crypto in some ways. Crypto's still happening.
Sorry, it's not even crypto. It was Bitcoin. Blockchain.
Bitcoin.
It was blockchain, wasn't it? It's blockchain this, blockchain that.
Still there.
Oh, is it?
Yeah.
And again, technology, it's a valid technology. It's just being overhyped by, the crypto bros, I do feel the AI is becoming, I see it especially on like that platform formerly known as Twitter, where there's just a lot of AI snake oil being sold out there or, shared.
And that's what it is. It's all just marketing hype. And there are very real things about it, but by and large, it's not a gimmick anymore. It started off as a marketing gimmick, and it's not anymore. It's very real, but it is also, people are worried about artificial general intelligence. Skynet. Computers becoming sentient, things like that. We're 400 quadrillion connection. We're nowhere near this, right? And the AI we're doing right now, it's very artificial, but it is not intelligent. It's just a math model.
Right. It's still just predictive stuff.
It's a predictive math model.
Right.
There's people are still working on true artificial intelligence, but it's a ways away.
It was something that came up at BioIT World, or whatever we called the convention, that amazing convention in Boston last year. Was that they were sort of lamenting the fact that people, even when they weren't focused on the AI, they were feeling that they had to mention it because stockholders or whatever people wanted to hear that because that was going to up their value or whatever. But the reality is in the space, in this bio IT space, you're saying that obviously it's not the solution to everything.
No,
but it's getting more of the attention because of that, because of its sort of popularity now.
I have lots of conversations about building HPC infrastructure.
Right.
And people are like, we need to buy all the GPUs, which NVIDIA loves.
Yeah.
Right. And even AMD's starting to love because they're selling really good ones too.
Oh, are they really? I didn't realize they got into the game.
Yeah.
Oh, okay.
Yeah. The MI series, those are great. They're
really?
Great.
Okay. Right.
And a lot less expensive than NVIDIA right now. But they're saying we need to buy all the GPUs and because AI, it's everything. And I'm like, no, it's not. It's 15% of your workloads.
Right.
15. Right. And only 30% of life sciences codes, if I'm being generous, a friend of mine reminded me last week that I'm being generous with that, can even work on GPUs. Because GPUs are not just fast processors, they're a completely different type of processor, right? Our standard CPUs, work on logic, they're logic gates, right? GPUs run on vectors. So direction and force essentially is what those run on. So eigenmath, matrices, things like that. That's what GPUs run on. And so if your code is very sort of integer counting based, it's really hard to do that on a GPU, and it won't make it faster.
Right.
So you have to make your code work there. Things like matrix math, which is all of AI, work really well on. So,
right.
Which is why it accelerates it. And keep in mind they were meant for graphics, which is why they're vector processors.
Right.
Because graphics in motion are vectors. So, that's.
It's funny. I was sort of introduced to those processors because I think it was during the pandemic they became very expensive. I ended up buying NVIDIA because I thought, oh my God, there's such a huge demand for gaming GPUs.
Yeah.
And I fluked into buying the stock before it took off for the AI stuff, which was amazing. But
that's a happy accident.
But it does feel very much like, was it the black tulip bulbs back in whenever it was? Like it feels like a bubble. Like it feels like we're overhyping it. But there's still stuff. I mean, it's still there was a Nobel Prize given for AI's use of something to do with
neural networks.
Neural networks. That was it. Right.
Yeah, deep neural networks, which is when most people talk about AI these days. That's what they're talking about.
Right.
So, large language models, GPT, all that. They're giant, deep neural networks.
So, do you get scientists or groups calling you up and saying, "We want AI to solve this problem," and you have to go, "Okay, here's the thing." No, they're.
I get people calling me up and saying, "We need to do the AI."
Oh no! Really?
Yeah, for real.
Wow! Wow! So you got like my mom's calling you.
Remember when I was talking about the computational sophistication earlier?
Really?
Yeah, it comes to bear. And they're like, well, everyone else is doing it. It's like, yeah. What do you need to do it for? I don't know. We just need to do it. So
wow.
This is not everybody.
No.
Some organizations are like, okay, we need an LLM for this.
Right.
And I say, no, you need a SLM for that, a small language model. Right? You don't need, to spend $100 million creating this thing. You can spend 1,000 and it'll do the same thing, right? Or, sort of this, I guess the latest rage or agentic workflows, right? So, series of agents that modify the output of something like an LLM to check it. Like, is this real? Let's check.
Right.
So is it a hallucination or not? What's the accuracy of this thing? What's the context of this? And so running things through agent workflows is much more approachable.
That's neat. Yeah.
It's very cool, actually. Some of my staff educated me on this just a couple of months ago, and I was like, whoa, that's pretty cool. So, there's a lot of different applications, a lot of different ways to do it. Everyone just kind of runs into the giant fire that it's burning. Like well, we got to do it. And
Yeah.
everyone wants to be ChatGPT now. It's like, no, the LLMs, large language models, are not fit for everything.
Right.
There's a lot of different other types of analytics that'll work. Some of them not even AI. And so it's I think what we're trying to do is, I guess, responsible use of AI, like realistic.
Right.
Yes, let's use this. Yes, let's figure out where it's good. Yes, it'll help everyone. It's going to help us innovate because we're going to be able to spend time on different things. People are like, oh, it's going to replace interns. No, there's always a need for interns, right? They might do different things, but
I love
our conversations about replacing actors. Right?
Yeah, I mean, again, this is the fun thing is I feel like there's a possibility that all this stuff could come true, but at the same time, there's also this aspect of it for me where I go like, what do I want it to do? Like someone there was a great quote. Someone said like, I want it to do my laundry. I don't want it to do my art. You know what I mean? Like, I want to do the art, so I want it to do the laundry so I can do the art. You know what I mean?
Yeah.
I use it a lot with programming. I love it with programming because I'm not someone who uses one programming language. I play with this stuff, although Python seems to have just taken over for me now. That's all I use. I've been recently playing with, you'd like this, I've been playing with some data analytics of data visualization stuff, and I've been trying to get Python to import this data on science projects, at science fair projects, into Blender and have it generate these 3D structures based around just from the data that's coming in. So much fun. But I wouldn't be able to do it without ChatGPT, or Copilot. I mean, that's
because it's complex programming, right? And ChatGPT was, the model was trained on basically the entire internet and then some. And so it's got context that we don't.
Well, and the syntax, I mean, it's so perfect for programming to me because it's just a syntax thing, right? It's just like, that was always, once you get a sense of programming, even just for myself, once I get a sense of how to program, you can basically apply that to any language. You have to learn the various different, specific foibles of the language as you go. And ChatGPT is so good at just telling you, yeah, you idiot, you missed a colon there, or you should have indented that, or whatever. So
Well, then that there's going to be more and more tools coming out to help with programming.
Right.
So like GitHub Copilot, I think, or Microsoft. There's two different kinds. But it's just going to be incorporated into whatever you develop in.
Yeah.
You're going to just query a thing. I need to do this. Here's your code. Right. And then you go look at it to make sure it's actually going to work, and edit it because it won't always just work.
Right. Well, that's the other thing is there's some stuff it just gets totally wrong. But again, as a tool, it's just it's fantastic. Is this? Do you mind if can I launch into some questions that people have?
I was going to ask if we should. I mean,
actually,
we're in one of our
Our timing is actually very good. Normally, I babble for about an hour with people, and then we do questions. And we're just coming in on the hour. And when do you need to run away? Let me know because
about 25 minutes or so.
Okay, great. All right. Well, you just let me know, and we can bounce you off. And but in the meantime, all right. Concerned asks. Modern science is computationally heavy, and a lot of the algorithms for these processes are inefficient. Would quantum computing help with stuff like this?
I'm going to golf clap that question.
That
is a great question.
I was happy to hear it. Yep.
Yeah. I'm going to split that into two pieces.
Okay.
Reality and Schrodinger's world.
Okay.
Which
he's killing the cat. He's killing the cat.
Is he though? I don't know. Maybe.
Hey, where is he? Yeah, exactly.
So the first part of the question is algorithms. We keep throwing more hardware at bad code and inefficient code. We could be doing far more research on how to do algorithms differently, to be more efficient, to use less power, to move more quickly, those sorts of things. People don't do it. They may make some code that works. They may update it. They might, but they'll just use that forever. And let's throw more stuff at it, more hardware, right? That's a problem. AI in particular, that's a big problem. I forget who did this projection, but they said that AI on its current curve by 2027 will consume 134 terawatts of power. I mean,
they were worried about crypto.
Yeah, crypto is nothing. This will actually warm the planet legitimately, right? And we don't have enough power to power that, right? So if we're gonna give something up, it'll be that, right? Or fix the algorithms. All right, now the second part of that question, quantum computing.
I'm going to mute myself because there's a truck backing up behind me here.
Oh, okay, I can't hear it. So, but quantum computing. So I do kind of joke, and I've got a lot of friends in the quantum industry. So if you're watching, sorry, but I call it Schrodinger's compute. It both exists and doesn't at the same time. It's funny because Stargate addressed this a whole bunch, which is kind of funny, right? Which was
nice getting that in there. Well done, well done. Yep.
But it's true, right? I mean, your writers were always talking about, we don't understand quantum mechanics on this level. We've met other groups who do things like that, right?
Yeah.
We don't understand enough to really do quantum computing on an individual atomic level, and so we're averaging. They're essentially big probability machines at this point. We're getting better at it. I do think that they'll help in certain things. And one of the things that came out of the supercomputing last week for me, and also a conference I went to a few months ago in New York City, HPC and AI on Wall Street, is that quantum computing is not going to be its own standalone thing. It's probably going to be like a coprocessor, like a GPU.
Oh, interesting.
Right? Attached to a larger machine that does certain things really well.
Right.
But it's probably not going to be its own standalone thing.
Yeah, because we're always looking for one solution, aren't we? We're always looking for that one thing. Like you say, with your absolutism with the cloud or the not cloud. We want like our one thing that's going to fix whatever it ails us. And you're saying is that we're just going to be able to have all these different ways of breaking down a problem.
Yeah, which is really how it should be.
Yeah.
Right?
Yeah.
Not everything's suited to everything. That's there's no accounting for taste. Well, there's no accounting for algorithms.
Right.
Right. I think that there's what we really need to get towards is application aware specificity and what algorithms work best where, and to have a constellation.
And what's required for that? What do we need to make that happen? Is it just people need to care more about the algorithms they're using, or?
I think we need to do like efficiency research on, what actually works best. We don't know because we're going so fast because someone needs to get funded, and you gotta get more money for the research, and you gotta, always be building things, and then there's all this marketing coming at us, and we don't know what's real and what's not. Let's hire experts like us. Okay, I love that. However, it'd be nice to focus on more problems than what you have to buy, next week, to actually get ahead of it and to be like, okay, let's handle all of our data in a similar way because we don't. Let's make it all sort of available in good ways because it's not, and then let's plug in all of our computing around the data so that the data is what's at the center,
right?
And the different tools you can use to look at the data and analyze it and turn it into knowledge, because that's the point, are sort of plugged into it somewhere. All the stuff on the cloud, a TPU is a great example, right? The tensor processing unit.
Oh, right. Yeah. That handles the AI specifically, right?
I think I'm screwing up which cloud it is, but I think it's Google's cloud that has that. But they're tensor cores. TensorFlow is the library that that does deep neural network training, right? And so they have these specialized ASICs, these chips, built with TensorFlow, and those are TPUs. So that's specialized hardware to go and do something much more efficiently than you can do it on a standard computer. And so, use things for what they're good at. And not everyone force everything into a GPU, or everything force everything into a CPU, or everything force everything into, carrier pigeons, whatever.
Right.
Or quantum, to get back to that question.
So the quantum, you're saying the algorithms need to be improved. Then what is the other side of the quantum issue there, you're saying?
We need to understand how it works.
Right. Okay.
Right. How to code for it.
Yeah.
and also that field needs to converge. I think there's 12 different types of quantum processors that they're all trying to align around a qubit, right? A quantum bit, right? And we can't ever see a quantum bit because we just don't have the technology to do it. So now they're talking about logical quantum bits, which are averages of a bunch of things that are probably this, right?
Wow.
And so it's a probabilistic math model operating in something that can operate at the speed of light or faster. And with multiple states, by the way, it's not just ones and zeros, it's 1 through 5 in some cases, right?
Because you can have the different spins and all the different
spins, different excitability, different electron valences, different bindings, or you're binding two together or pulling them apart and annealing, right? That's all these different things going on, and
but we'll get to a point with the quantum computers, I'm assuming, that we don't, I don't know the ins and outs of everything about the processors I'm using, but I get the basic understanding. I feel like even with the quantum stuff, are we ever going to get to a point where we go well, yeah, I get it makes sense. We got,
maybe.
It's just, it seems
that's
so.
That's why I call it Schrodinger's compute.
Yeah,
maybe.
Right, there you go.
There's a lot of maybes there. It will drive forward our understanding of quantum mechanics, and that is a good thing. Right? That is a great thing.
Well, and encryption seems to be a big part of it too, right? Isn't that what they're worried about?
I heard someone talking about quantum proof encryption.
Yes. Yeah.
Right. Not even quantum can break this. And so we're getting ahead of a problem before it exists. It's sort of like Y2K.
Yeah. I remember it well.
Happened. Some people will say, well, that's because we prepared so much.
Yeah.
And other people are like, okay, but what if we had done nothing? Would it still have been such a big catastrophe?
Right. But again, the news is not a plane landed safely in Brussels today, right? I mean, it's not, and all the passengers were happy. Anything else you want to add on the quantum stuff, or I got another question?
I can add. I can go on forever, but let's answer your question.
Is your company working with quantum stuff yet, or is that not? It's not really on the.
Not really.
Not really yet.
We're.
You got to be aware of it, but you're not actually
watching it, especially in life sciences. There's some people trying to do some genomics work on it and kind of figuring it out. And one place where it'll likely be very helpful is in simulations.
Right, of course. Yeah. Well, because if you're trying to simulate in a quantum world, why not use quantum computing, I suppose, yeah.
Yeah, quantum resolution is matrix math, right? And, linear algebra is all what simulations are built on. So,
wow. So you basically have to know a little bit about everything.
Yes.
Or no, actually, I'm going to go further than that. A lot about everything.
It's one of the cool things about consulting, actually, is that you're just exposed to so much all the time.
Right. Yeah. Look, it's the same reason why I like the acting, is I get to do different things all the time. I get to learn different things as I go along. Not quite the same. Nixie's got a question for you. Fabulous Nixie says, in our lifetime, computers have changed so much. Where do you see computing being in 50 years' time? Oh, great question. Yeah, what do you got? Crystal ball. I'm not going to hold you to it. Not a prediction. Just what do you think? What's your sense?
The question is almost unanswerable.
Right.
Because we are approaching a limit of what we can do with silicon.
Mm-hmm.
Okay. The pathways are getting smaller and smaller and smaller on CPUs to the point where electricity running through a silicon chip is no longer going to work.
Right.
And so, there are lots of laws, I guess, that surround that.
You mean like laws of physics and things?
Laws of physics, and also rules around computing, right?
Right.
So there's Moore's law, which is basically the doubling of technology.
Is that still going? Is that still valid?
Everyone's pretty sure we're past Moore's law at this point.
Oh, okay.
Where technology has gone way faster and gotten a lot cheaper, far beyond that curve.
Wow. Okay.
And so.
Well, I just thought we wouldn't be able to keep up, but I guess it's the opposite then. Okay, great.
No, we far exceed.
Wow.
So.
Okay.
But anyway.
Is there anything looking forward? Is there anything that you're excited about? Is there anything is there a future technology that you go like, oh man, can't wait to get my hands on that?
I kind of remain a skeptic with these things, right? Because I've been in technology for so long.
Right.
There are things that I think are really potentially exciting. Okay, so one thing that I don't know if 50 years is enough time, but something that would be really, really cool is quantum networking. And that is the concept of entangling atoms at a distance and using that for instant communication across any
Instantaneous networking.
Instantaneous.
Wow.
Right, and they are messing with it. The Department of Energy is playing with this, doing quantum entangling and then separating atoms by lots of distances, and kind of being able to look at those. It's the same problem that we have with quantum computing, but again, if you can resolve those twitches into ones and zeros, you can transmit data that way.
And it wouldn't matter how far. You could literally have a network on the moon, and there'd be no lag, nothing.
No lag, zero.
Oh, okay. I'm with you. I'm with you. I like that. I like that.
Mars, we don't know that there's a limit to this, right?
Right. The quantum stuff is just fascinating. We had one of Agnes' friends on. I called her the Quantum Queen. And she was explaining some of the stuff that they've been playing with. It's just amazing. I can't get my head around it. Hey, Gimpy G. Okay, Gimpy G Gaming says, Lance, is Moore's Law a thing of the past? Oh, we literally just did this. Home PC is not doubling computing. Okay, so I think we've kind of addressed that already. But so he was basically saying, is Moore's Law a thing of the past? You're saying yes.
It is.
But he's saying home PCs are not doubling in computing power every 6 months anymore. So consumer technology maybe isn't doubling.
No, yeah. Part of that is driven by economics, though.
Right. Okay. All right. That's not a technology thing. That's an economics thing.
No, it's both. Because the things that are still doubling or more have power requirements that your house can't do.
Right.
Or are so loud that you can't do it. Or the only way to keep them cool is with direct liquid cooling, which you can do in a small space in your really high-powered gaming PCs. But the giant pump things that we showed you at TAC, keeping the Frontera
with the mineral oils, trying to keep things
exactly right. The immersion cooling, things like that. But at the same time, we are approaching kind of this flat space where there's just not a lot you can do with silicon.
Right. All right, so you're right, Lance. I ruined your question. I apologize. This is the problem with having. The problem is Lance and I know each other too well, so we're asking each other questions.
No, it was a good question.
That's why I got to it first. Just AP Kilby asks. Now you got time for this? We got time for one more?
Yeah, we can do a few more. Yeah.
Oh, good. Okay. How does the CPU and GPU affect integrated neural networks like the ones found in smartphones and ARM PCs? Let me ask that again for myself. How does the CPU and GPU affect integrated neural engines like the ones found in smartphones and ARM PCs? I don't know that I understand that question.
Can
you explain the question to me?
Okay, so if I'm interpreting the question right, what we're trying to differentiate here is the difference between training a neural network and using a neural network. Right? So it's training and inference. Right? Inference is those neural network chips or algorithms or whatever that are on your phone. So it unlocks with your face. That's a chip that has that neural network already programmed into it on your phone. Utilizes some data on the back end, right?
This is the edge computing that they talk about?
No. It's just inference, right?
Oh, okay.
All right. You have a model. So when you're using ChatGPT, the model's already been created. You're using the inference of ChatGPT to get your answer.
Okay.
Right?
All right. Okay.
So it's the result of training a neural network.
Right. Okay.
And so how CPUs and GPUs affect that? Depending on the neural network, most often inference is a lot cheaper to do than the training is. Right? Using the model takes way less power, is much faster than creating the network in the first place.
Right.
And so you can build them into things. You can just make it a software thing. Maybe this is what the question's getting at, which is, if you've got a CPU and a GPU on there, can you offload inference, to the GPU while the CPU is doing things? Probably, you can do that. But some things still require their own accelerators just to happen in real time. So, like computer vision, for instance, what Tesla's working on with autonomous vehicles, or even just recognizing, hey, there's a person in front of you, stop. Things like that. That has to be encoded on chips. It's too much going on for it to be in software.
Yeah, you can't be reliant on any kind of like a network or anything for that.
No, you can't.
And that's also your small language models too, right? That would apply because you don't. Why have a massive, huge model when you only need to be looking at certain slices of the world?
Yeah, I mean, large language models are great for like chatbots, right? For instance, which are really helpful for customer service.
Are they? I've had a few run-ins with them. That's all.
Sure. Okay.
Yes, badly designed
really
ones are terrible, right? But yes, yeah.
They need to still kick out to humans at some point.
Yes.
Instead of replacing humans.
Look, I love the idea. If it's a simple solution that can be given to you quickly, then of course. Yeah. But the problem is that I guess most of the times I get into tech support, it's you're at like a stage where you're like, I've done the off and on. What the hell?
Right.
Yeah.
Yes. Skip to stage 92.
Yeah.
Done all things, right. You need cheat codes in the chat.
Yeah. That's it. That's it. Yeah. Press pound, whatever.
Yeah. Press pound star back and forth 15 times and then 8.
Right. And you'll get an actual human.
Yes, exactly.
Are you using any AI on any? Are you using Apple AI or any of these?
Not really.
No.
We're starting to use it in Zoom, so the transcription services are really cool.
Oh, right. Yeah, of course. Yeah.
I use Grammarly.
But that's got to be difficult though, because if you've got such a if you're talking about like HP, like high power computing stuff and bioinformatics and bio stuff. Surely the code's not going to be able to keep up with some of those words, right?
It mixes some stuff up. It depends on the model, right? Certain terminologies get screwed up, but so it's not perfect. But this is why you have to go back and edit it. And when two people are talking over each other, it has a hard time pulling those apart. But
right,
or if there's a lot of noise in the background, but. It certainly is much better than me sitting here having to do real-time transcription.
Oh yeah, which just doesn't get done. I mean, this is my thing: is that a lot of the AI stuff that I love about it is that it's allowing me to do things that I just would never have done before because I wouldn't have time.
Yep, exactly. It should allow us, to get ever higher on Maslow's hierarchy of needs, right?
Right. Yeah, there you go.
More to self-actualization. Focus on the cool stuff. Let AI do some of this stuff.
Right. Yeah, that's it. Yeah, do the laundry. Damn it. It's funny. I played recently with I had to do an audition and the sound wasn't great, so I ran it through the auto AI thingamadoodle that's in Adobe, and I was listening to it and I was like, that sounds pretty good. And then I went, wait a second, I didn't say that.
Yes.
It actually changed. It changed butterflies to botflies, and something, and I'm like, whoa, oh my God, it's literally, it sounded exactly like me. It took out the background hum, but I guess what words it didn't know what they were, it just it made it up. I was blown away. I mean, I thought it was amazing, but at the same time I was like, that's not helping me.
At least you caught that.
Yeah. Well, because I was thinking it was just a simple filter. I didn't realize it was literally recreating words for me in the process.
You want to watch a really masterful use of combination of actors and AI in film. David Blass just put something out, Star Trek Universe. Unification, and it's a short film. It's on YouTube, and basically
it's called Unification.
Convincingly used AI art and actors to recreate people who aren't even here anymore.
Wow!
Act new parts. It's really something.
Wow!
It's a little disturbing, but it's also really something. Anyway, that's an interesting. Should we answer one more question?
It's amazing. Let's see. I think we may be out of questions. Let's have a look. We've stumped them all.
We talked about all the things.
Yeah, we've covered everything. That's it. No. Okay.
Yeah.
Well, let me just see if there's any. The Stargate technology seemed like entanglement. Yeah, the entanglement thing is just fascinating. Absolutely, that is so sci-fi in every way. It's amazing. There is one thing I'd love to talk to you about because it's another thing that I'm actually fascinated by, which you have which is a pet project for you as well, which is the idea of taking all of this disparate data that's out there and creating a system for dealing with that. The idea of having, like, my God, how amazing would it be to have all this data in a form that we can use, and you're trying to come up with a solution for that.
Yeah, we are.
It sounds like it's defeated you. It's
no,
like, yeah.
So back to something we talked about a lot earlier, which was that data is sort of all over the place. Especially in life sciences. The problem with that is that when someone's trying to pull different data sets together to do a more powerful analysis, they have to spend 80% of their time just getting those data into the same context to even be able to analyze it.
Yeah.
Right. And so one of the things we want to see happen is to unify this data ecosystem. When anything is labeled red, it means red, right? Where some people might use a 1 for red. Some people might use an R. Some people might use RD. Some people might use D. I mean,
or an RGB or a hex code or a
a hex code right, or the name of their daughter. Whatever, right? That's called metadata. It's the data that describes data. And that needs to be unified so that you understand the context of things.
Right.
And then the file formats need to be unified so that you can just directly compare the files. And on some level, you need a really low level architecture for that.
Right.
The lowest level architecture that we use every day is an operating system.
Right.
So on some level, you need kind of a data operating system, something low level that kind of handles a lot of that data unity and then lets everyone have their own tools plugged into it. Right.
Right.
And really passionate about that. It's really hard to do. We've been.
It's so cool, though. The idea of that is so appealing to me. Even just from my silly little science fair project stuff, just trying to, even within years, they're calling things different things. Like they're referring to, it's bioinformatics one day, and then it's biocomputing or whatever the next. I mean, it's like, I wonder if I said so. But there's no standard to any of this stuff.
No, there are some sciences that have done it really well. Let's talk about astronomy for just 1 second.
Oh, interesting.
To get going, because they had to figure it out, right? The Earth is spinning. And so they were watching something and suddenly it go out of view. They'd have to hand it off to another observatory somewhere, to watch it, to keep observing it as the Earth spun. And so, they developed common, metadata standards, 50 years ago. We
could still fuck up the imperial and the metric, though, right? I mean, that's still
we're really good at that.
Yeah.
I mean, here in the U.S., we like our feet, inches.
Yeah, you don't make it easy, do you? Yeah.
Yards.
But the scientific community is basically, isn't it all metric at this point?
It's all metric. Yeah.
Yeah.
Because that's a universal language, and it kind of makes sense.
So a data operating system. So this would be a system. Yeah. So basically, it would unify all of this different data. You'd have a standard approach to everything from MRIs to images of the sun type thing.
At the most basic level, I don't know that we know enough to do it across all disciplines at this point.
Okay. So you're right. Okay.
It would probably have to be per science domain.
But even just the biology side of it would be amazing. Yeah.
I mean, imagine you could walk into a hospital in, I don't know, Denmark, then come home to wherever you are in Austin, Texas, and your medical files are there already in a language that everyone understands,
right.
And you don't have to farm it out, get it translated, all those things. Because most medical systems use their totally different annotations. So your medical history is sort of scattered around.
And would this be like an open source type thing, I'm assuming? Something that you'd...
Oh, definitely. Yeah.
It'd have to be, basically.
We're not a product company. We don't pretend to be. We never will be.
Right.
But in order for this to make a real impact, it would have to be open source and create a community around it.
I love it. Where are you at with it? What's the? I mean, is it?
We got kind of a prototype operating with the National Institute for Minority Health and Disparities at NIH.
Oh wow!
They've got
is this something that people can play with?
No, not yet.
Oh, okay.
It's a very narrow community that they're starting with. It's a specialized data set, but it's we're in the process of we're trying to get it out into production for them. But the NIH is sort of funding the initial ideas of this under that particular program, which is called SHARE, SCHARE.
Right.
But it's the nucleus for this idea.
Right. You can't call it DOS because they've already taken that. We've already got DOS.
And data operating system's already been taken too.
Yeah. Oh, has it really?
Yeah. So we have to find a good word for it. Maybe we should do a contest.
Yeah. See who else? Yeah. See, let's
non-trademarked word for it.
Yeah, non-trademark words for a data operating system that isn't DOS or whatever. Should I let you out of here? You got to run.
Yeah, I probably should get going. But, this has been great. Thank you for having me on.
All right. As always, an absolute pleasure. I feel like we'll have a million more of these. Yeah, thank you so much for taking the time. I know you are a busy man, and I appreciate it very much.
It's my pleasure, and thanks everyone for tuning in. And it's
yeah, indeed. Thank you for the great questions. Indeed.
Yeah, good questions.
If people want to find out more information, what BioTeam?
BioTeam.net.
BioTeam.net, yeah, and it's a great site. There's a lot of stuff going on there, so yeah, definitely people should check that out. And if there's someone's in research, something wants to get in touch with you, same thing, just go to the website and get in touch there. Okay.
We have info@bioteam.net that goes to all the right people, and
fantastic. Amazing. All right. Thank you so much. I will wrap it up with you, and I will also wrap up the stream at the same time. So until we geek again, folks, be brave, be kind, be brilliant. Thank you again, Ari, and we'll.